Let's consider how to draw the Lewis structure for the carbonate ion CO3 2-. First, we need to figure out how many valence electrons there are that come from the carbon, from the oxygen, and from the 2-. To do this, we go to the periodic table and we count 1, 2, 3, 4 valence electrons for the carbon. It's in the fourth column. It's also 4 more electrons than the previous noble gas. And we also find that oxygen is in this sixth column. So oxygen has 6 valence electrons. Now, another thing we can note is that oxygen is to the right of carbon. Elements that are up and to the right on the periodic table are more electronegative. So that means oxygen is more electronegative than carbon. Since carbon's less electronegative than oxygen, it's likely to be the central atom for this polyatomic anion. So using this information, we can tally the number of valence electrons. Each carbon, there's only one of them, has 4 valence electrons, so that's 4 from the carbon. The 3 oxygens each have 6 electrons in their valence shells, that's 18 valence electrons. And then finally there's this 2- charge, so that means that above and beyond the counts from carbon and oxygen as neutral atoms, we're going to have 2 additional electrons. So if we add all of this together, we get 24 valence electrons. Now, each of the elements wants to surround itself with a certain number of electrons. If that element is hydrogen or helium, it wants to fulfill what's called the Duet Rule. It wants to have 2 valence electrons surrounding it. If it's carbon or oxygen or many other main group elements, it wants to fulfill what's called the Octet Rule. It wants to have 8 electrons surrounding it. Carbon, since there's one of them, wants to be surrounded by 8 electrons, and oxygen wants to be surrounded by 24. So that's 32 electrons overall that they would like to have surrounding them, those nuclei. Now, since we have a desire to have more electrons than we actually have valence electrons, what we can do is engage in bonding to share electrons and meet those needs. So bonding electrons are just going to be the difference of these two numbers. They're going to be 32 minus 24. That's equal to 8. So that's 8 bonding electrons. And we would predict that's actually 4 bonds, because each bond is 2 bonding electrons. Okay, so let's write out all the different elements with their starting number of electrons, valence electrons, as dots surrounding them to kick off our Lewis structure. So here's carbon as our central atom with 4 valence electrons surrounding it. Each oxygen is surrounded by 6 valence electrons to start, and we want to start filling octets. Now remember, we're supposed to have 4 bonds, so a really easy guess here would be that we're going to have 1 bond per oxygen to start off with that. Another thing we should note here is that if I just count valence electrons to make sure I haven't done any funny business, I'm going to be wrong. Check this out. So I have 6, 6, and 6, that's 18, and then 4, so that's 22. I'm missing 2 valence electrons. I have to add a couple in. Why? Because they come from the 2- charge. So I'll just throw them in there for now, and we'll see what happens. The 2- charge is 2 extra electrons above and beyond the neutral elements. So I have to throw 2 more dots in there. And we'll kind of remedy whether or not we need to do anything later on. So, or like where they're going to go later on. So I'm just going to draw a couple bonds. So those 2 electrons became a bond. Those 2 electrons became a bond. Those 2 electrons became a bond. Let's see what's going on with the octets. So the octet for this oxygen is not filled because it has 5 non-bonding electrons and 2 bonding electrons, so that's 7. Actually, it's the same story for this one as well. This one needs another bond. So does this one. This oxygen has a complete octet. Check it out. It has 6 lone pair electrons, 6 non-bonding electrons, and it has 2 bonding electrons. So this one's done. For this one, I need another bond. So what I'm going to do is erase 2 electrons, one from the carbon, one from the oxygen, and draw in a bond. Now its octet's filled because this oxygen has 2 4 non-bonding electrons and 2 4 bonding electrons. That's 8 electrons total. This oxygen, however, is still stuck at 7, and it wants to be surrounded by 8 bonding electrons. So I'm going to have to erase this electron and this electron on the carbon and put in another double bond. So let's check that out. So there's something wrong with this. I'm going through like doing things wrong just to make sure that you see where errors come in. So notice that carbon has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 electrons. That's not allowed. Carbon's in the second row of the periodic table. It can't have more than 8 electrons surrounding it. So that won't work. We have to go back. So we still want to fill a valence shell for oxygen, and actually it looks like we have 2, 4, 6, 8, 9 electrons around carbon, so that electron has to go away. We need an electron over on that oxygen on the left, so that's how you remedy this. Wherever we had put those 2 extra electrons, it wouldn't have mattered as long as we just make sure that the octets are filled and that we're not putting more electrons that are allowed for second row elements from the periodic table. So now carbon has 2, 4, 6, 8 bonding electrons. That's good. Its octet's filled. This oxygen has a filled octet with 6 non-bonding electrons and 2 bonding electrons. And so does this oxygen. This oxygen has a filled octet as well. Let's do some formal charges and see what's going on. So the formal charge for carbon is going to be 4, that's the number of valence electrons we start with, minus the number of non-bonding electrons on it, in this case 0. There aren't any like lone pairs on carbon. All the electrons in the valence shell of carbon are involved in bonds. And then you also subtract out the number of bonding electrons, in this case 8 because there's 4 bonds, divided by 2. This is accounting for electrons, and the way this formal charge thing works is it's kind of like saying, hey, every bond is like 1 electron to one element that's in the bond and 1 electron to the other element that's in the bond. That's why you take the total number and divide it by 2. You're dividing up the bonding electrons accounting style between different elements. So if I do the math on this, I get a formal charge on carbon of 0. For these 2 oxygens, the ones with single bonds, I'll just give them a subscript of 1. I get that there are 6 valence electrons we start with, minus there's 6 lone pair electrons, and those aren't participating in bonding. And they also have 2 bonding electrons. You divide those by 2 when you're calculating formal charge. You end up getting that they each have a -1 charge. So each of these oxygens has a -1 charge. And then finally, for the double bonded oxygen, we can repeat this calculation. We get that the formal charge for this double bonded oxygen, I'll call it O2, is equal to 6 again, because I'm just writing the number of valence electrons in a neutral oxygen atom. Then I'm going to subtract out the non-bonding electrons, and I'm also going to tally the, well, actually 1/2 of the bonding electrons involved in those 2 bonds, the double bond. So that's going to be 6 minus 6, which is 0. So this has a formal charge of 0. This carbon has a formal charge of 0. What's the overall charge? -2. This is great. We wanted to have a -2 overall charge. That's what's in our polyatomic anion that's given, and we've confirmed that using formal charges. Finally, we can try to figure out what the geometry of this polyatomic anion is going to be. The way you do this is you just count the number of places that electrons are located around the central atom. There are 3 places: this bond, this double bond, this single bond. So when there are 3 places that electrons are located around a central atom, that's going to be a parent geometry of trigonal planar. And since all three positions have an element, it's just trigonal planar. Trigonal planar is flat. It's a 120-degree angle. So the geometry is going to look like this. You're going to have an O, oops, sorry, a carbon, then an O, an O, an O, and each of these angles is going to be 120. You can draw in double bonds or single bonds as you like, but that's the geometry. So this molecule looks flat. If I draw the molecule and I put it into 3D software, what ends up happening is I get a flat plane for all four atoms, all four nuclei. And it's flat. It's got a 120-degree angle, and there's no like up-down asymmetry to it. It's flat. So that's trigonal planar. That's the Lewis structure and the geometry via valence shell electron pair repulsion theory for the carbonate anion.